All right. So thank you for coming. My name is Yoni. I'm the gameplay team lead for Play Studios Europe. I have been a programmer for 12 years, solely in the gaming field. I've been building games both professionally and recreationally. And today I was lucky enough to talk not about work, but about my passion, which is specifically retro games. And more to the point, how simple math makes them amazing. And my goal here is to get you to understand that I suffered in high school and university math, and it was only when I got to the gaming world I realized what a gem I had in my hands. And that's my goal here in this talk, to hopefully get you to my side. So I'll start by saying that game developers are not programmers. Okay? Server developers are programmers, or architecture developers. Game developers are technical artists. We use the math as our brush, and knowing and understanding that, we're able to create incredible games, even with simple math knowledge. So in order to demonstrate this bombastic claim I made, I'm going to talk about pseudo 3D. Okay, it's a concept that was widely acknowledged in retro gaming. Today it's kind of lost, because today we have true 3D. And this is my way of getting you into this point. So what is pseudo 3D? Pseudo 3D is a technique which causes images and scenes to look as if they're three-dimensional, when in fact they aren't. None of the data structures that you're using gives you any indication that this could be three-dimensional. It's only by trickery that you make it appear so. So let's begin by talking about the difference between true 3D, the similarities between true 3D and pseudo 3D. Okay, so I don't know how much experience any of you have with 3D engines, but in the core of it, you have a virtual space, some void, endless space, and within it, you've got a camera, which is your perspective to this void, and you've also got points scattered around this void. Okay, they're referred to as vertices. Okay, vertices are the basis for displaying anything on screen in a 3D world. And the whole 3D pipeline, in a nutshell, is finding a way to translate those 3D points in space to a pixel on your screen, a two-dimensional pixel. So as it says, each frame rendered to the screen takes into account all the vertices currently seen by your camera, as we can see in this little thing here. All right, you've got your little guy walking around, and he's looking at two-dimensional top-down view of vertices in space with lines connecting them. And then we can see what he sees. All right, so these vertices are translated to the camera view, and their 3D world position is converted to 2D screen space, because at the end of the day, we're watching a 2D screen. Okay? Now, what are the differences then between pseudo 3D and true 3D? Well, this is a nice example here. You've got pseudo 3D on the top and true 3D on the bottom. So on the bottom, you've got a mesh, okay, a real 3D mesh made of points in space that make up this nice little mountain. And each point, you can imagine that it has an X value, a Y value, and a Z value. It's an actual point in 3D space, okay? Whereas the one on the top, if you look simply on the left, you can see that we have a two-dimensional map with a top-down view. The only information we have in pseudo 3D is always an X and a Y. That's it. And we're going to somehow turn that into a 3D perspective that we see on the right. Okay? And because pseudo 3D encompasses a lot of different projects, there is no industry standard as there is today for true 3D. Okay, it's usually the same model, view, projection, matrix that you work with. Here, things tend to vary between projects that you're dealing with. Now, pseudo 3D used to be very, very prevalent. Okay, PCs in the 90s were shit, and in the 80s even more so. And the only thing that was powerful enough to display graphics on screen used to be arcade machines. All right, and save for very, very limited examples, the vast majority were pseudo 3D games. All right, so you've got your Outrun and your Afterburner and your Hang-On, and I don't know if you guys played these games ever, but they were extremely popular and fun, still fun today. And all of them were generated from two-dimensional data. and they use some kind of trickery to cause them to look three-dimensional. And of course, Wolfenstein, which is the case example we'll be talking about today, is no different. It also has only two-dimensional data. However, it was the first game that did this for PC, which is why it was considered so revolutionary. And it also opened up the first-person shooter genre. So Wolfenstein was created by mainly these two people, John Carmack and John Romero, two geniuses really that beforehand had other several breakthroughs in the PC world. For instance, Dangerous Dave on the right, I don't know if you played it, amazing game. It was the first time that they managed to get a PC to render a platform game. Okay, and if any of you have played the Dangerous Dave, when you move from one screen to the other, then it just switches to a different screen, maybe like the first Prince of Persia. That was breakthrough in its time because no computer could render anything like that, and they fixed it by fixing the screens. And after that, they were working on a game called Commander Keen, also extremely popular, which was the first platformer to allow the background to scroll with you. And this was insane in the late 80s, beginning 90s. But they wanted to push the envelope even further, and so they created Wolfenstein 3D. So Wolfenstein 3D is a game that has you controlling a captured Allied special agent in World War II. He needs to escape the castle, kill as many Nazis as possible. And it was a huge success. It was the first time that anyone had ever seen anything like this on a computer screen or anywhere really. And it blew people's minds. It was immersive in a way that nothing came close to beforehand. It was so successful that it made $200,000 a month in those. The industry back then was very small. This was considered unbelievable. And the way it managed to do this was through a technological breakthrough called ray casting. Now, John Carmack did not invent it, but he did turn to university papers that spoke about this theoretically, and he managed to actually translate it to an actual working product on the PC. And in this lecture, I'm going to briefly explain the inner workings of ray casting. Okay, so before we get started, there's a few concepts that we need to align ourselves to, and that's things that we need as prerequisites to understanding what's going on. The first of it is right angle triangles. I'm sure all of you are familiar with that. You've got your right angle triangle with the angle theta, then you've got the adjacent part, the opposite part, and the hypotenuse between them. And the second thing we all need to just be aware of is the angles that we're working with, okay, 0 on the right, 180 on the left, and our XY coordinate system, which starts from the top left, because we're working in a 2D screen, and they usually work like this. The second is the Pythagorean theorem. All right, we've got 3 squares here, and we can see that they have a triangle in the middle that they create, and the area of the one on the left and the bottom is equal to the area of the one on top. Or the square of that gives you the length of the hypotenuse. This lies in the core of everything I'm about to show you soon. Next is, well, how radians work. So you've got a graphic here of a circle, you've got the radius of the circle, and if we take this radius and we actually stretch it on the circle, you'll see that 3.14 approximately is half a circle, and 6.28 is a full circle. So the radius of a circle is 6.28, its radius. All right? Let's finish. Wonderful. Okay, now how do we put all of this together? We put all this together using, again, this is high school math. You've got your sine and cosine and tangent. So a sine of an angle will give you the height of its opposite, and the cosine of an angle will give you the width of its adjacent part, and the Pythagorean theorem of those two will give you the hypotenuse that you're working with. And also, there's a neat little function called arctangent that any decent computer software will allow you to do, which is when you decrement the top of the hypotenuse from the bottom, you will get the angle in radians, and those are all extremely useful for any kind of game. Now, just how useful are they? Before I go on to that, and the last part is 2 degrees. If you want to create any game at all, you need to understand the basic concept of 2 degrees. It doesn't matter if you're playing a 3D game on your PlayStation, or if you're running Mario or Candy Crush, at the end of the day, behind the engine, it's always working with grids in some way or another. Okay, so as the Candy Crush or strategy games or Mario or Diablo or Tetris, they all work with grids under the scenes. Before we proceed, let's just talk about things we take for granted, because there are very, very thick books that have been written about Wolfenstein, and we're not going to dive into everything that they cover. We are going to take things for granted today. For instance, our ability to easily write pixels to the screen. That's not something that was taken for granted back then. Or the fact that we have powerful hardware, or that we don't have any issues with the keyboard input. We're simply going to talk about the logic. Okay? All right, let's begin. So first and foremost, from the image I showed you earlier, how we take a 2D scene and extrapolate it to a 3D projection. We begin with a 2D grid. Okay, so we got this little guy walking around the grid, and we need to keep track of where he is at any given moment. We can do that easily by getting the integer value of where he is divided by what's known as the tile size. Okay, you can see all the tiles in the screen are of the same size, width, and height, so we can always just divide it and get the integer value, and that's where he is on the screen. And we can also create a map this way. All right, you can see the data set I'm using behind the scene is just this matrix of ones and zeros. One, I mean, you can't see it here, but one would be like a wall, and zero would be the floor, and P would be the initial place player. Okay, so it's simply a matter of translating this matrix to an image. Next, we have our player, okay, and he's inside of this grid that we just constructed, and he needs to turn around. Okay, so you need to be able to define some rotation on this player, again in radians as we showed earlier with the circle. And you also have something called the field of view. Okay, all of us have a field of view as humans. Okay, if my hand is here, I don't see it. If it's here, I do see it. It comes into my field of view. And you can see you define this as a variable. For instance, here it's 30 degrees in to the left or the right of where I'm currently looking at. And I turn around and I can see the field of view rotating with me. Okay. The next thing that we're talking about is the projection plane size, which is simply the screen we're working with. Let's say we're working with an 800 by 600 pixel screen. So that will be the projection plane size. Okay. And the technique called raycasting that we'll be talking about in a moment requires us to take a field of view and fire a ray. I know that means nothing yet, but we're going to fire 800 rays for 800 horizontal pixels of the screen. We'll see what that means in a moment, and that will give us the image that we're looking at. Okay? So it's time to talk about raycasting. So raycasting transforms a limited form of data, okay, into a 3D projection. It traces rays from the player's viewpoint to the surrounding world, okay? And each column of the screen, that's what we spoke about a minute ago, corresponds to a point in space relating to the player, okay? So the rays are shot from the player's position until they hit something. Okay, I know this is all Chinese, and let's see what this means in a moment, okay? So this is a ray. What you're looking at now is a ray, all right? You've got your grid. Let's say this is a grid that's much smaller than the grid we just saw, because here every pixel is one pixel. It's not a tile of 100 pixels. And we are currently firing a ray. That means we begin in our player's position in the direction that he's looking to, and we are increasing by one pixel some kind of ray. Imagine it's a bullet that you're shooting out. So the bullet increases by its position by one pixel every time you update the function. Okay? Now, you can see that what you're getting here is a hypotenuse of a triangle when you get down to it. Okay? So if I'm standing here in a certain direction, I begin this ray casting loop, which simply says, okay, I'm here, let's move one pixel forward, let's move one pixel forward. Did I hit anything? No. Move one pixel forward. Did I hit anything? No. And it just works like this recursively until you hit something. So how do you even increase this ray? By simply increasing the hypotenuse of the triangle. You make it bigger and bigger and bigger and bigger, and this is your ray. It's actually just the hypotenuse of a triangle. That's it. Okay? In fact, this method of doing things is so ingrained in how it is you make games that take any game whatsoever. Again, doesn't matter if it's 2D or 3D or whatever, from the 90s, from the 80s, from 2 minutes ago. If you have a unit on screen and say it has a speed of 5, right? You have a tank, and there is a motorcycle, the motorcycle has a speed of 10, and you want it to move forward in any direction that it's facing, all that's happening behind the scenes is that you're creating a hypotenuse of a triangle, and you're using the sine and cosine functions to get its position on the next frame. So if the speed is 10, the hypotenuse is 10, and then sine of that will give you the y, and cosine of that will give you the x, and that's its position on the next frame. That's it. Okay. And as I just mentioned earlier, we need to run this code in a loop. Okay? We need to advance our ray in a loop until we hit something, until the hypotenuse is long enough for actually hitting a wall or something. Okay? Okay, so so the wall distance, as we said, is the length of the ray. If we finally hit the wall, that's how far it is away from us. Okay? And as I said, if our viewing angle is 60 degrees and we need to fire 800 rays for those 60 degrees, okay? So we fire the ray here, we hit something. We fire the ray here, we hit something. So when we finally do hit something, we know which ray it is. So we know what column on the screen it is, okay? If we hit something here, that's the left part of the screen. If we hit something there, that's the right part of the screen. If we hit in the center, that's the center of the screen. So we know what ray corresponds to what column of the screen pixels, okay? And so we know how far it is away. We know what ray it is in the pixel columns. What we don't know is, okay, what does that mean? How big, if I want to take this data and now draw a wall, the 2D wall that I hit on screen, how big should that wall be? So the way to determine that, and this is actually where I told you the difference between pseudo 3D and true 3D, is that you have three-dimensional data for every vertex in space. Here, we had X and Y. What we don't have is the Z, or in our case, the Y. We don't have the height of the wall. So the answer is that we get it at runtime. We extrapolate this data from the length of the ray, okay? So in order to do that, we need another variable, something called range of sight, okay? What is my range of sight? Say that you are now standing on a mountain and you're looking out to the distance. Your range of sight is the distance, okay? Everything from the distance up to you is well, in your brain, scaled according to how close it is to you, according to that range of sight. Okay, if something is at the range of sight, it's at 0 pixels. You cannot see it. And if it's right in front of you, it takes up your entire field of view. So once you've defined that, you just have to divide the distance by that, and you've got the height of the wall. Okay, and you can play around with this range of sight. You can make it bigger or smaller, and the wall will scale accordingly because it will take up a different percentage within the range of sight. Anyway. Okay, so now that we have that, we can actually draw our walls.
I actually have a question. You said it's a loop.
Yes.
But if we put a loop in another loop, also known as matrix, can we solve the 3D in that way? For example, if I have a ray that's going straight,
yes, and
it will encounter this board here behind it.
Yes.
In 3D, would I know the angle for it, even if I have the higher one? So okay. It's verifying left to the right, as I understood.
Okay.
So how do they figure it out from the top to bottom to get the third dimension?
So as I said, there is no third dimension in space. Okay, it's not that every point only has 2 dimensions to it. The third dimension is trickery. It only exists in the projection to the screen. All right, we hit a wall. We know how far it is. We've decided what our range of sight is, and then we can say, okay, so the farther it is, the smaller it is.
So we're using the range of sight and the distance from the object to scale it.
Yes, and we're playing around with each range of sight until we get a value that we like. And what we end up with is just the number of pixels that it should take on our screen. We also center them, so it's always in the middle. All right, but the farther the wall away is, the smaller it is, the closer it is, the bigger it is, and that's it. Okay, and we fire 800 pixels in case 800 rays for 800 pixels if that's what we're dealing with, and we have our scene. Okay, now our code works, but it's awful. All right, why is it awful? Because we are incrementing our ray by 1 pixel for every single ray, and we're firing 800 rays. So these are hundreds of thousands of iterations, which will make this game, crash an old system and run very, very slowly on our current system. So don't do this. This is just so it's simplified. So there are ways of optimizing this and actually reducing the number of iterations drastically. And we can do this because there are two things that we know. First, we know what direction we are facing. Okay, we've got our circle. As we were talking about earlier, our radius is 6.28 times the circumference is 6.28 the radius of the circle. We know that 0 is on the right, pi is on the left, and 2 pi is the entire circle. And that way we can know where we're facing. Okay, right is this, up is that. We know which way we're facing. That is important. The second thing which is important is that our tile-based grid consists of equally spaced tiles. They are all 100 pixels high and wide. There is no out-of-place tile, which allows you to make assumptions. And these assumptions can let you take shortcuts. Okay? So when we're standing inside of a grid, okay, we know the distance from where we are to the end of the current tile. Okay? That's one thing that we know. And from that point on, we also know the distance of all the other tiles. It's 100 by 100. Okay? So we just have to figure out how to get out of our tile. Okay? So we don't actually have to jump 1 pixel at a time. We can actually jump fixed intervals because the grid is of a fixed size. So once we figure out what this interval should be, we can just jump that. Okay? So we're going to talk about a worse way and then a better way afterwards. So the first way is that we only have to calculate how to get to the next grid intersection, right? So in the previous example, we know that we might either want to intersect with the next grid vertical line or the next grid horizontal line. And for each one of those, we have one piece of data. We have either the width or the height of the triangle. And what we need is the other axis to either intersect with the vertical rows or the horizontal rows. And for that, we use the tangent function. Okay, so we take the tangent of the angle and we either multiply it or divide it by the data that we have to get the other axis that we are currently missing. And that will allow us to know where we need to jump to. Okay, now, as I said, you can either intersect with a horizontal line or a vertical line. You can see this animation shows two triangles. And what you do is you simply take the shorter one. So you find the next intersection with horizontal, with vertical, you try both triangles, you see which is smaller, you advance there. And you continue going on and on and on, each time with the next intersection with the grid, until you finally hit a wall. And bam, we've reduced this from hundreds to what? 4. Okay? So extremely optimized right there and then. However, we can even do better than that. Okay, even that is not optimized enough. You can optimize it even further. And in this animation, you can see that I'm drawing two lines. The first one intersects only with vertical lines, and the second one intersects only with horizontal lines. And the reason this is better, okay, is because what you have to realize is that once we've escaped our little box, all of the next deltas are identical to each other. Okay, whether you're going from one vertical line to the other, each of these line segments are exactly the same length as the one before them, once you've escaped the confines of your box, whether you're intersecting with horizontal lines or vertical lines. So you don't need to calculate two triangles on every iteration. I mean, the Pythagorean theorem is still expensive in that sense. Once you have your initial one, it's just incrementing the delta. It's a simple addition function, and you run both of them in a while loop until both of them hit something, and you take the shorter one, and that's it, right? And again, we've reduced this not in the amount of iterations that we run, but in the complexity that we take each time. Okay, simple addition is of course far easier, and this is the solution that Wolfenstein actually took. Okay, and this is our result. Right, so we have our 2D data of the player. rotating around the world, and we take the rays that he's firing from left to right, and we simply scale them. I also added some coloring here to make it apparent, but something is wrong here. I don't know if you can notice it, but there's something called the fishbowl effect that's happening here, okay? The walls are not straight. You can notice it very clearly when we're right in front of this white wall. It's got this kind of curvature to it, all right? And it might be unnoticeable, sometimes it's really noticeable, but we'll explain this phenomenon and we'll fix it, okay? So what's happening here is that, as we said, we're firing 800 rays. And whenever a ray hits something, we take the length of the ray and we use that to understand what the wall height is. But if you'll notice, the rays on the left and right are longer than the rays right in front, okay? So obviously, the walls on the left and right are going to be smaller because they really are farther away as far as the ray is concerned. So now there's a calculation that we use to correct this. Okay, and this calculation is that you multiply the distance again by the cosine difference of the forward angle minus the angle that you're looking at. So it'll be forward minus this, forward minus this, forward minus this. But each time the delta gets bigger, I think, and until you get to a point where the wall is completely straight. Okay, so now that we've taken that into account, we can go back to wanted textures on the walls. And when you think about it, we already have all of the data that we need in order to texture our walls. It's just a matter of realizing it, okay? So why is that? We know where our ray is going. We know if it's going left, right, top, bottom, and we can figure out the distance of where we hit to the last grid intersection. So the grid has a fixed size, okay? So if a grid line begins here and I hit there, I know what's the distance from where I hit to the beginning of the tile. I know this, okay? So if I know this, I can work out the percentage of the ray within the tile. So I can work out the percentage of the pixel that I have to sample within the image. Okay. So that's what's known as texture mapping. Okay, as I just mentioned, we're firing an array. We hit this tile. We know that tiles are, for instance, 40 pixels long. So we know that we hit on, I don't know, 46. It doesn't match the image, but never mind. And we can divide that, and we know that we need to sample the column at 15% of whatever it is we're doing. Again, there's a mismatch between what you're saying and what's written, but you get the picture of it. So all we need to do now is, when we're going to render this column on screen, instead of just putting a color there, we can just map our texture of the image at column 15. Okay. Now, you're not limited to one wall, obviously. You have your 2D grid, and you can decide, all right, 1 is a blue wall, and 2 is a wood wall, and 3 is a jail cell, and so on, so on, so on. Okay, so it's just the image that you're sampling and the column that you're taking. So with that in mind, they released another game called Catacomb 3D, and it was also not a big success. No one cared about it, and this time, when they were thinking about it, they decided it was probably just didn't have any shock value. Okay, they wanted something that would, cause to people to take interest, and so they swapped things around and they changed the theme with the exact same code, and they came up with Wolfenstein. I don't have an image of that yet, but Wolfenstein was a huge success, as we previously mentioned. How far along are we?
15 more minutes.
15 more minutes. Okay, so that's the end of Wolfenstein. Okay, Wolfenstein did not have ceilings and floors. It did have tiles. So I got through the ray casting part. That's over. I can continue a little bit just to talk to you about sprites and floors and ceilings, if you find it interesting. Let's begin with sprites. Okay, so this is where another big difference between true 3D and pseudo 3D manifests itself. Okay, on the right we have a true 3D dolphin. It's made of points in space. Each point has x, y, and z values. Okay, but obviously you can't do that in pseudo 3D because again we're working with a 2D data set, which means that in all of pseudo 3D games, even Doom, for instance, which is still pseudo 3D, I hope you guys have played the original one, then every time you come across a sprite, a lamp, a potted plant, a desk, or people, it's just a 2D image, which has been overlaid and scaled accordingly. Scaled similarly to how we scaled the walls, but there are no meshes, which is why in all of these games, if you rotate around the enemy, he's always looking at you if they use one sprite. Okay, so regardless where you are, you're seeing the same image. So how do we do this? How do we draw sprites to the scene? So we draw them as is, right? It's just an image that you need to know where to put. And you scale it, same as you scaled the wall, right? It's the range of sight divided by the distance to the asset, just as the wall was. Okay, and then of course you can decide whether you want to scale it internally, up or down, depending on how high it is. The thing is that we had one iteration for all of the arrays, for all the walls, and then we have another iteration for the sprites that are within our field of view, which means that they'll be painted above everything else. So you also need to keep track of where you're drawing over the walls, and then run the ray casting again for the specific area. Not a big overhead, it's fine. Drawing enemies and characters. So we just mentioned it's exactly the same as furniture. Only you can use tiled images, you can use sprite sheet data, and as I said, it's of course you could change the angle of viewing. You just need, for instance, 36 images for each angle, and if they're walking, then it's that multiplied by the number of angles that you want to be viewing them from. So in most of these games, they'll simply come at you. Last thing is character AI. This is really nothing to do with Wolfenstein. This is very, very basic. In every game that you play, characters like NPCs will have this radius that activates them. They might have this endless loop of patrolling something, and only when they're interrupted, then they'll come at you. And this is done by defining a radius for the enemy that alerts him. So again, it's simply circles and triangles and radians once again, and when our player comes into range, then he starts moving towards him. We were talking about the arctangent function earlier, so that's exactly how this works. It just calculates the hypotenuse from the blue to the red circle and starts moving towards him according to the speed that was defined on him. Okay, this is the part I like the most. Floor casting and ceiling casting. Okay, so Wolfenstein did not have floor casting. It was too costly for them to do at the time with the hardware they had. But there was another platform, the Super Nintendo back then, which had dedicated hardware for this, and this did this really, really well. Now, in subsequent games like Doom, they did use floor and ceiling casting, so we can talk about this. It's a neat little thing. Okay, and the idea is very simple. Okay, so you've got an image on the left, a static image, and there is a player inside. We've seen that before, and he's walking around on this image, like this tiny little man walking on an image, and he's got his field of view that we've established earlier. Only here, you can see that we're defining the distance that we talked about earlier, right? And you can actually see it. You can see where his line of sight begins, which is the line closer to him, and when this loops over, you'll see over again, we're going to see this is the range of sight. Okay, so he cannot see anywhere past further the outer line, and you can see on the right it shows exactly what he's showing here, and I'm going to increase the distance that he's seeing, and suddenly the horizon reveals itself. Yes. Now, what is actually going on here? The thing is, this is extremely simple. What we have here is a projection from a trapeze to a square. All right? You've got this little man on the image, and the trapeze that we've defined defines his field of view. And all you have to do is realize what are the pixels encapsulated within that trapeze. And you simply say, I'm going to take this trapeze and I'm going to project it to this square at the bottom part of the screen. And the pixel at the top left of the trapeze is going to be the pixel on top of the screen. And I'm going to go row by row over the trapeze and simply fill it in the square. Okay, basic projection from one shape to another. I think this is amazing. This is like magic. And this is the end result of a little Wolfenstein clone I did that has floor casting and ceiling casting and lamps and enemies coming at you. And that's it. Thank you.
So we have 5 more minutes, so you can ask some questions if you have.
Okay, so if I remember correctly, there is a mission in Doom in which there is an elevator, essentially, and there's an enemy on top of the elevator. Now, we know it's 2D still, because if you shoot the enemy, even when he's up or below you, you're still gonna hit him and he dies.
That's right.
But how do they pull it off to make it seem like it's a moving object going vertically up and down?
Okay, so let's start by saying Doom is not my specialty. I'm working on it these days on the next lecture. But the thing with Doom is that if you look at the maps that they generated, they were also 2D maps. They only used 2D data. And what they did was, if here, all the walls are the same height. Okay, that means that when you finally hit the ray, the wall is simply the distance divided by the range of sight, which takes into an assumption that they're all the same height. That's like the missing component to take for granted. So in Doom, what they did is they had this ingenious algorithm called binary space partitioning, which allowed you to split the map up into sectors. And each sector had metadata attached to it that said what was the wall height within that sector. Okay, so that's, first of all, why the maps are much, much more interesting. And secondly, you still, as I said, you have only 2 axes of data. You were not limited on top down. So you could add sector data, meaning that you've got a loopy floor height that just gets, not floor, yeah, a wall height that gets higher and lower. That's how they pulled this off.
Or for instance, like in Catacomb, that they just wipe out.
Yes, definitely. All right.
What's the case when something is transparent? For example, glass or water. For example, I know there's a glass wall in front of me and there's a wall behind. And me as a player character would see both walls. But how would we solve that?
Okay, so that's not a problem. All right, like we said, we have a tile map. All right, 1 is a blue wall, 2 is a green wall, and so on and so on. And our code knows to stop when it hits a wall. So you could simply say, if the wall that you've hit is of type X, keep going. All right, that's how you pull it up. That's how they did doors, for instance, right? You have doors between rooms. So if when the door is open, it's still a door tile. So if the tile you hit is of type X, keep going. All right, that's that. Anyone else?
Is it very possible to add shadows?
Shadows. What do you mean by shadows?
Well,
Shadows for what?
well, maybe for the furniture, for those enemies.
So again, all of the you can see that the plotted plants and the character, he does have the hidden shadow. It's just part of the image, right? You have transparent or semi-transparent pixels as baked as part of the PNG image. That's one thing. If you're talking about real illumination, that's a very, very different topic. What else? You again?
Specifically, when it comes to designing AI, in this case, you pulled us out a very most basic type of AI. So is it worth it adding field of vision to the AI in these types of games, or is it too taxing and demanding on the PC?
Play around with it. Play around with it. This is all trial and error. Whatever works.
Is there someone where we can download this presentation?
The presentation, no, this whole thing is recorded on YouTube.
On YouTube.
And my source code is on GitHub. It's on the blog and it's there. Okay? There's nothing
Yeah,
else.
we don't have time more, so that's it.
Thank you very much, guys. It was a pleasure.